Welcome to the video lecture on angles and their measure. An angle AOB consists of two rays, R1 and R2, with a common vertex O. So this is how an angle would be drawn. We've got our ray R1, our ray R2, and there's 3 points, A, O, B. The middle letter is always the vertex, so the O is the center, and your initial side would be the ray 1, your terminal side would be the ray 2, and our angle goes from the initial to the terminal side. If you are dealing with a positive angle, then you always want to go in the counterclockwise direction. So your initial side would have to be down here on the bottom, and our terminal side would be up here on the top, so that we're going in the counterclockwise direction. If we started with an initial side over here and a terminal side on the left, and we go down in the clockwise direction, then this would be considered a negative angle. So the measure of an angle is the amount of rotation about this vertex required to move ray 1 into ray 2. And there's 2 different units of measurement that we commonly use for an angle. The first one is degrees, and the second one is radians. So degrees are defined to be 1 degree is equivalent to rotating the initial side 1 out of 360th of a complete revolution. Radians is the amount that an angle opens measured along the arc of a circle of radius 1 with its center at the vertex of the angle. So what this implies is if you have that unit circle, which means it has a radius of 1, then the amount that the angle opens measured along the arc of a circle with its center at the vertex of the angle would be this picture right here, where the angle is this theta right here and the arc is this t. And in the case of a unit circle, the theta, this sort of central angle right here, which is in radians, equals to this arc length t, which is also in radians. So on our unit circle, it's true that this central angle theta will measure the same amount as this arc length going around the edge. But that assumes that you are on a circle of radius 1. So when we're trying to convert between these 2 different units of measurement for angles, we want to keep in mind this simple ratio, or this simple fact, that there are 180 degrees in pi radians. Or you could also use the fact that 360 degrees is equivalent to 2 pi radians, 1 revolution. 180 to pi is what I'm going to use just to give us a simpler conversion factor. So if I'm going to convert degrees to radians, then all I have to do is multiply by pi over 180. And if I want to convert from radians to degrees, then all I have to do is multiply by 180 over pi. So for example, if I have 30 degrees and I want to convert that to radians, I'm just going to use the appropriate conversion factor. And if I have degrees and I want to get rid of it, I'm going to put the degrees on the bottom so that those units would kind of cancel out. And then I want radians on top so that I'm left with it after I'm finished reducing. And we know that there are pi radians in 180 degrees. So when I go to reduce, 30 goes into 180 6 times, so this is going to reduce to pi over 6. So 30 degrees is the same as pi over 6 radians. Now if we take pi over 5, that's already in radians, so to convert it to degrees, this time I'd want to put the radians unit on the bottom and put the degrees unit on the top. So I want to put the pi on the bottom and the 180 on the top, and this time the pi's will cancel out, and 5 divides into 180 36 times. So we would be left with 36 degrees. Okay, so be able to convert back and forth between degrees and radians just using the conversion factor pi over 180 or 180 over pi. Now we say that an angle is in standard position if its vertex is at the origin and its initial side is on the positive x-axis. So you always want the initial side of your angle to line up with that positive x-axis, and the vertex of your angle is at the origin. If it's a positive angle, then remember we're going to go counterclockwise, so our terminal side would be maybe over here. And if we're talking about a negative angle, then we'd want to go clockwise. So our initial side still starts on that positive x-axis, but then the angle would sweep going down in that clockwise direction. Another vocabulary word that you're going to hear is the word coterminal. So we talk about two angles being coterminal if their sides coincide. So their initial sides have to match and their terminal sides have to match. So on this angle here, my initial side is always on that positive x-axis and my terminal side would be up here. So the angle that I'm talking about would be this swept angle right there. Let's call it theta. Now we would say that that angle theta is coterminal to this angle going around in this direction. So again, still starting with my initial side on the positive x-axis and having a terminal side up here. So my initial and terminal sides match what I had over here, but this time I'm sweeping that angle in the clockwise direction. So if I call that angle alpha, then we say that alpha and theta are coterminal. Another option would be to again let your initial side be on that positive x-axis, let your terminal side be up here, and this time go in the counterclockwise direction, but do it in more than one revolution. So in other words, sweep all the way around one complete revolution, but then keep going until you hit that terminal side again. So that would give you another coterminal angle. What we want to realize is that if you are coterminal, that means that the two angles are within multiples of 360 degrees. So if we want to figure out two angles that are coterminal, then all we're going to have to do is add or subtract multiples of 360 degrees. So for example, if I wanted to start with the angle that was 160 degrees, and I wanted to find an angle that was coterminal with it, that was positive, then a real easy way to do that would be to take 160 degrees and add one multiple of 360 to it. So add one revolution, and that would give me 520 degrees. And you can kind of visualize what that would look like. Here's that 160 degrees. It's slightly less than 180. So 520 would go all the way around once. There's that 360, and then we go an additional 160. So this blue revolution here is the 520 degrees. So that's what I mean by coterminal. So we would say that 160 and 520 are coterminal. Now how could we get a negative angle that's coterminal with 160 degrees? Well, you just start with 160, but this time instead of adding 360, we could subtract 360 from it. And we're going to end up with a negative angle here, negative 200 degrees. So if we draw a picture of that, again, here's our 160, this amount right here. And then this time, we're going from this initial side clockwise to that terminal side, and that would be that negative 200 degrees. So negative 160 and negative 200 would be considered coterminal. So all you have to do is add or subtract multiples of 360 to get multiple coterminal angles. So let's try one more example. We want to find an angle that is coterminal with 1300 degrees. So if we start with 1300 degrees, we could just go ahead and find one single coterminal angle by just subtracting off or adding. You could add also here, but I'm going to try to make this angle get smaller. I'm going to go ahead and subtract off one revolution. So if I subtract off 360 degrees, then 940 degrees would be coterminal. Let's keep going. Let's subtract another 360, so another revolution. Then we would be down to 580 degrees. If I keep subtracting here, another 360, finally I get down to 220 degrees, which is less than 360, so this would be less than one revolution around. Not that you have to do that, but it's just kind of nice to know what 1300 degrees is equivalent to without all these extra revolutions. So what would be our answer here for coterminal angle? Well, what's coterminal to 1300? You could write 940, or you could write 580, or you could write 220. There's an infinite number of possibilities here. Okay? Now next we're going to talk about a formula for the arc length of a circle. So if we have an angle whose radian measure is theta, and it's subtended by an arc that is the fraction theta over 2 pi of the circumference of the circle. Let's kind of draw a picture for what all that fancy talk is really trying to represent here. So let's draw a circle. We have a circle. This time it's just a general circle with a generic radius r, not necessarily a unit circle. The theta is this central angle here with its vertex at the origin and its initial side on that positive x-axis. And the arc length is going to be this piece right here, this length along the edge of the circle. So if you think about this, what fraction of one full revolution does this theta sweep out? Well, if theta is in radians, and we are always going to assume whenever we use this formula that the theta we're using is always in radians, okay, you have to assume that, then the fraction of the full revolution that theta sweeps out is its theta out of 2 pi. So this is sort of the fraction of one full revolution. So what would our arc length be here, this s? Well, the arc length is a fraction of the entire circumference. And what fraction would it be? Well, it's the same fraction that this angle represents. So we're going to take this fraction, theta out of 2 pi, and we're going to multiply it by the circumference of the entire circle to find out what fraction this arc length is of the circumference of the whole circle. So what's the formula for circumference of a circle? It's 2 pi r. So when we take our fraction theta out of 2 pi and we multiply it by the entire circumference, 2 pi r, the 2 pi's cancel and we just get theta r. So here's our formula for arc length. The arc length of a circle, s, is the radius times the angle theta. And this assumes that theta is in radians. This formula is not true if you are using a theta that's in degrees. Okay, so arc length of a circle, s, is equal to r theta. So let's put this into practice. Let's find the length of the arc of a circle with radius equal to 10 that subtends an angle of 60 degrees. So what that means, if we draw our circle, we have a circle this time with a radius of 10, and it's subtending an angle of 60 degrees. That just means that this central angle here is 60 degrees. And we're trying to find this arc length right here, which I'm going to call s. So according to our formula, this s should be our radius, which we know is 10, times our angle, which we know is 60 degrees. The problem is that this 60 degrees is not in radians. So first we have to convert 60 degrees to radians. And hopefully you already know what that is, but in case you don't, we're just going to do our conversion factor, put degrees on the bottom, radians on the top, pi radians in 180 degrees, 60 goes into 183 times, so 60 degrees is the same as pi over 3 radians. So to find out what this s is, I'm just going to use my radius of 10 times my theta, but I'm using the theta in radians, so that's pi over 3. So this arc length is 10 times pi, or 10 pi, all over 3. And what are the units on our arc length? Our arc length is also measured in radians as well. So this distance here is also in radians. Now just a quick note here, back to our formula for arc length. If this was a unit circle, just to remind you, and we mentioned this earlier in the lecture, if this was a unit circle, then your radius would be 1. So on a unit circle, this radius would be 1, so that means your arc length s is equivalent to this angle theta. So this angle inside would match that arc length if you're on a unit circle. If you're not on a unit circle, then you kind of scale or multiply by that radius. Okay? Let's try another example. Find the measure of a central angle of a circle subtended by an arc of length 8 if the radius of the circle is 4. So let's draw a picture. Here's my circle. We have this time, we're trying to find the central angle. So this time we're looking for this theta. We don't know what theta is. We know that it's subtended by an arc of length 8. So that's talking about the arc length. And the arc length is this piece of your circle right here. So that's normally what we call our S. And we know that it's equal to 8 in this problem. And the radius of our circle is 4. So according to our formula, S equals r theta. We know what our S is. Our S is 8. We know what our radius is. Our radius is 4. And we're looking for theta. So all we have to do is divide by 4, and we get theta is 2. And what would be the units on this theta? Well, it's always radians. So this central angle theta would be 2 radians. Now let's talk about a similar looking formula. This time, instead of talking about arc length created by an arc and a central angle, now we're going to talk about the area of a sector. So we're going to imagine taking our circle here of radius r with this central angle theta, and this time we're going to try and figure out what the area of this sector right here would be. Okay, so that area right there. So if our central angle here is theta, remember that theta sweeps out an angle that's a fraction theta out of 2 pi. So it's theta out of 2 pi for one full revolution. That's the fraction of one complete revolution that theta sweeps out. So if we take that fraction and multiply it by the area of a full circle, then we will know what fraction this little wedge is out of the area of the full circle. So it would be like taking 1/4 of the entire circle if theta was 90 degrees, for example. So first we find out what fraction our angle makes out of the entire revolution, and we multiply that by the entire area of a circle, and the area formula of a circle is pi r squared. So if we multiply theta over 2 pi times pi r squared, the pi's cancel, and we're left with 1/2 r squared equals to theta. So A, the area, equals 1/2 r squared theta, and again this assumes that theta is in radians. So this is for the area of a sector, a little wedge of pi from our circle. So let's find the area of a sector of a circle with central angle of 1 radian and the radius of the circle being 5 inches. So if we draw a picture here, we have a circle with a radius of 5 inches, and the central angle here is 1 radian, and we're trying to find this area of that whole little wedge. So our formula is A equals 1/2 r squared theta. We're looking for A. We know what our radius is. Our radius is 5 inches. We want to square that radius, and our theta is 1 radian, and that's in radians already, so I don't need to do any conversion. I'm just going to write a 1 right here. 5 squared is 25, so this is going to be 25 divided by 2, or 12.5. And what would the units on this be? Well, remember, it's an area, so we're talking about squared units, and since the radius was in inches, this is going to be inches squared. Okay, let's try another one. Find the area of the sector of a circle of radius 2 feet formed by an angle of 30 degrees. So we're taking a circle, we're creating a 30-degree angle right here. The radius is 2 feet, and we want the area of this little wedge. So our formula is A equals 1/2 r squared theta. We're looking for A. We know what our r is. It's 2 feet. And before you plug in 30 for this angle, you have to remember that 30 degrees is an angle in degrees. So we're going to have to convert that to radians first. So pi radians into 100, or it is equivalent to 180 degrees. 30 goes into 180 6 times. So 30 degrees is equivalent to pi over 6 radians. So you want to be using pi over 6 in your formula for your radians. Then if we go to simplify, we get 1/2 times 4, which reduces to a 2. That 2 goes into this 6 3 times, so we're going to end up with pi over 3. And the units on this would be the squared units of your radius. So since my radius was in feet, and I'm squaring that radius, this would become feet squared. So area should always have squared units. Okay, one last example. We have a sector of a circle of radius 24 miles that has an area of 288 square miles. Find the central angle of the sector. So we have our circle. It has a radius of 24 miles, and we know that the area of this wedge right here, this sector, is 288. So what must this angle theta be right here? So our formula is A equals 1/2 r squared theta. This time I already know what the area is. It's this 288 square miles. So 288. I know what my radius is. It's 24. So we're just looking to solve for theta. Now if you take 24, square it, and divide that by 2, you end up getting 288 right back again. So when I divide both sides by 288, we get theta equals to 1. And it looks dimensionless because our radius was miles, and we're squaring that, and we get miles squared over here as well. So it looks like our units cancel out, but remember that your angle theta is always being measured in radians. Okay? Alright, the last thing we're going to talk about are a couple more formulas that relate to speeds. If you imagine a point moving along the edge of a circle, there are two ways to describe the motion of that point. We can talk about its linear speed, and we can talk about its angular speed. So linear speed is defined to be the rate at which the distance traveled is changing. So if you imagine a circle and you imagine a point on the edge of that circle, the arc length is this distance s right here. So the change in that distance over time is called your linear speed. So the notation we use for that is change in s. That's what that little triangle means. It stands for change. Change in s, or change in distance, over change in time. So that's called your linear speed. Now, if instead of looking at how this distance or this arc length changes, we could instead talk about how this central angle theta is changing, and that would be called your angular speed. So it's the rate at which this angle changes over time. So it would be measured using the change in theta over the change in time. So linear speed is this distance along the arc length, and angular speed is the change in the angle over time. Now, if a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t, we're going to let s equal r theta, that's our arc length, be the distance that the point travels in time t. So again, here's my picture. We're just talking about a generic circle with the radius of r. Its angle is theta, and it's mapping out a distance or a path along the edge of the circle that has a distance of s, that arc length s. And we know the relationship between these three things. The arc length s is equal to r theta. That was our arc length formula. So based on this sort of picture here, let's come up with a formula for our angular speed. Remember, our angular speed was change in theta over change in time. So we're going to write our angular speed formula as theta divided by t. Now this funny symbol right here is the Greek letter omega, and that's typically the letter that you see for angular speed, how the angle is changing. So we're going to define omega, the angular speed, to be theta over t, and we're going to define the linear speed, the velocity, to be s over t, so how this s changes over time. Okay? Now notice a relationship here. If we define this v to be s over t, distance over time, since we know that s is equal to r theta by our arc length formula, let's substitute in r theta for that s. So now our formula becomes r theta divided by t. Now what I'm going to do is just take that r and pull it out front, and that will leave me with just the theta over t. And theta over t is exactly what we're calling omega. So this gives us a new formula, a new relationship between how this arc length changes over time and how this angle changes over time. So it's a relationship between the velocity, this linear speed, and the angular speed. And here's what it looks like. The linear speed v is always equal to the radius r times omega, that angular speed. So this is the formula for the relationship between the angular and the linear speed. Okay, let's take a look at a common example that you'll probably see in your homework that you do for this course. This problem has a truck with a 48-inch diameter for its wheels, and it's traveling at 50 miles per hour. And for part A, we want to find the angular speed of the wheels in radians per minute. So let's think a little bit about what we're given in the problem and what it is we're trying to find. We have a truck with 48-inch diameter tires. So if its diameter is 48 inches, then what would be the radius of those wheels? Okay, so let's take a look at a common example that deals with linear speed and angular speed, and this problem is something you'll probably see in your homework. Suppose that we have a truck with 48-inch diameter wheels, and it's traveling at 50 miles per hour. Part A, we want to find the angular speed of the wheels in radians per minute. So let's think a little bit about what we are given in the problem and what it is we're trying to solve for here. We have a truck with 48-inch diameter tires. So if the diameter is 48 inches, then what must be the radius of those tires? Well, diameter is twice the radius, or in other words, the radius is half the diameter. So this tells us that the radius of our tires must be 24 inches. Then we have that the speed of this truck is 50 miles per hour. That's its velocity. And the truck is traveling in a straight line, so that's its linear speed. So this 50 miles per hour is our velocity v in miles per hour. And what we're trying to find is the angular speed, this omega that we have up here. So we're trying to find omega, and look at what we've got. We've got v, we've got r, and we're looking for omega, and we know the relationship between all three of those. So this is the formula that we're going to use to help us relate all three of these variables. So for part A, we're going to use v equals r times omega. Now we have a little bit of an issue here. We know our velocity is 50 miles per hour, but our radius is given to us in inches. So we're trying to compare miles for this velocity to inches for our radius, and those units don't match. So we need our units to match. So you could either change the miles to inches, or you could change inches to miles. It totally doesn't matter which way you do it. The other issue that we have with units is our final answer needs to be in radians per minute. And right now, out of these two variables up here for r and v, the only unit of time that I see a reference to is this hours. So I'm going to need to change hours into minutes. So the problem itself isn't very tricky in terms of what we're going to do. We know V, we know R, we're just trying to solve for W. The hard part is all this unit conversion and making sure that all of your units match and lead you towards the right answer and the right units in the end. So we're going to substitute in our velocity V, which was 50 miles per hour. And remember, we wanted to change those hours to minutes. So I'm going to have to put hours on top so that these would cancel out and minutes on the bottom. We know that in 1 hour there are 60 minutes. And if we reduce this, 50 divided by 60, I'm just going to reduce that to 5/6. And that would now be miles per minute on the left side. So that's your V. Now for my radius R, I have 24 inches originally, but I need to change it to miles so that it matches the units on the left side of my equation. So we need to change inches to miles. So in order to do that, I'm going to have to use feet first. I'm putting inches on the bottom so they will cancel, and there's 12 inches in 1 foot. And then I know that if I put feet on the bottom and miles on the top, then the feet will cancel out, and there's 1 mile equivalent to 5,280 feet. So if I take all of that, see, 12 goes into 24 2 times, so this would be 2 over 5,280, and that's now miles. The only units I have left here after everything else is canceled out is just the miles. That's my R, and I need to multiply this by that omega. So here's my V, here's my R, here's my omega. So now to finish solving, we're going to divide both sides by this R. And notice that when you do that, what happens to your units? Since we have miles on top here and miles on top here, they're going to end up canceling each other out. And you're just going to have the minutes on the bottom. Doesn't appear that we have anything left on the top. We'll talk about that in a minute. And how do we simplify 5/6 divided by 2 over 5,280? That's just like taking 5/6 and multiplying by the reciprocal. So 5,280 divided by 2. So instead of dividing by this fraction, I could have just multiplied by the reciprocal. Same idea. So I could have done this on both sides. Now when you do that, 5 times 5,280 divided by 12, that turns out to come out to 2,200, nice and even. And we don't have any units left on the top for this omega, but remember what omega is. It's an angular speed. It measures how fast the angle rotates around over time, and our angle here is going to be measured in radians always. So the units on top, even though they don't appear to be there, are actually radians. So our angular speed omega is 2,200 radians per minute. So that would be our answer for part A. That's our angular speed. If you imagine a little point on the edge of that wheel spinning around, how fast that angle rotates. Now for part B, we want to figure out how many revolutions per minute do the wheels make. So we just figured out what the angular speed was, and notice that its units were radians per minute. So what we want to do now is just do a little conversion in the units, and instead of talking about radians per minute for that angular speed, I want to change that to revolutions per minute. So we're going to take the answer that we just got, 2,200 radians per minute, and we're just going to multiply that by a conversion factor. I want to get rid of the radians, so I'm going to put it on the bottom, and I want to change it to revolutions. So what's the conversion factor here? Well, we know that 1 revolution around a circle is equivalent to 2 pi radians. So if you take 2,200 and you divide that by 2 pi, use parentheses here, we get about 350. So this is approximately 350 revolutions per minute. So if you can imagine this tire for this truck, and you imagine just a little piece of gum stuck to the edge of that tire, because of how fast the truck is going and the radius of our tire and its angular speed, this little piece of gum is spinning around the edge of this circle 350 revolutions per minute. That's what we just figured out. Okay? So your final answer would be 350 revolutions per minute. Alright, that concludes our lecture on angles and their measure. Good luck!